In the first part of today's experiment, we are going to be actually testing the effect that the separation between the parallel plates of a capacitor it actually has on the capacitance. So for that matter, over here we have two circular conducting parallel plates that are placed on that following track. In addition, the track is actually equipped with a graduation or sort of with a ruler in order to detect the corresponding amount of separation that you are actually moving backwards by which one of these two plates. Now, in today's experiment, the aim would be actually to measure the capacitance of these two parallel plates capacitor as a function of distance. So in that case over here we have an LCR meter. An LCR meter that actually measures the inductance, the capacitance, and the resistance. And that's why, and that is actually what each initial stands for. So L stands for the inductance, C stands for the capacitance, and R stands for the resistance. But in our case today, our interest is going to be in finding the capacitance of a parallel plates capacitor. So first off, we are going to bring two electrical wires and we are going to connect them behind each parallel plate. So over here, we are going to bring the first connection and we are going to connect it behind that plate, and then we are going to bring the second electrical connection or the second electrical wire and we are going to connect it behind the opposite plate. Then these two connections are going to go into that LCR meter. So, like I have told you before, our target is going to be to determine the capacitance of that parallel plates capacitor as a function of distance. So each time we are going to be separating these two plates by a certain margin, or by steps of 0.5 centimeters or by steps of 1 centimeters. So over here on that graduation ruler, first off we can see over here that we have that index mark. We have that black index mark of the second plate. That index mark is located at 1 centimeter. In that case, we are going to consider the 1 centimeter to be our zero reference. So we are starting from 0, which is at 1 centimeter. Then let's say we are moving that plate backwards by a step of 0.5 centimeter. And then we are going to be recording over here the corresponding capacitance, which is at around 32.6 picofarad. So the unit in that case is picofarad. Then we are going to move that plate backwards by another 0.5 centimeters. So now we are at a total of 1 centimeter. And then you record the corresponding capacitance over here, which is around 20.7 picofarad. So as we can see, the more we increase the separation between these two plates, the capacitance is going to decrease furthermore. So if we keep going, let's say we move it backwards by another 0.5 centimeters. So now we are at a total of 1.5 centimeters. The capacitance is also going to keep on decreasing furthermore, and now we are at 15.3 picofarad. So the target over here is to cover the entire length of that ruler. Then we know from the mathematical equation which relates the capacitance to the distance that C is equal to K times A times epsilon 0 over D. But in our case over here, since the dielectric between these two plates is actually free space, therefore K is equal to 1, so we can get rid of. So C would be equal to A times epsilon 0 over D. So what we are actually determining is we are determining the values for the capacitance for a certain separation D between the plates. So as we can see, C and D, they are inversely proportional to each other. So in that case, later on in that experiment or in that report, they ask you over here to apply linear regression in order to determine the slope of C versus 1 over D. So the first part in the report, they are asking you to determine the slope of C versus 1 over D. Therefore, you have multiple values for D. You find their inverse, and then you find the slope of C versus 1 over D. Later on, after you find the slope, they ask you to deduce a value for the permittivity of free space. The permittivity of free space, in that case, it is actually an indication of the ability of free space to support an electric field. So we need to determine an experimental value for that epsilon 0, and we are going to deduce it from slope. But how are we going to deduce it from slope? First off, you have to identify an expression for slope. So over here we have slope of C versus 1 over D, meaning that C is the y variable and 1 over D would be your x variable. Therefore, in that case, whatever term that you have which is multiplied by x, you identify the terms that are multiplied by x, and that would be the expression of slope. So you have to identify, first of all, the expression of slope. After you identify the expression of slope, In that case, you can deduce a certain value for epsilon 0. Now furthermore, they ask you over here to find the error on epsilon 0. How can you find the error on epsilon 0? The error in that case is going to be propagational error. So epsilon 0 is going to be dependent on two variables. It's going to be dependent on slope, and it's going to be dependent also on the area. And the area in that case is going to be none other but the area of these plates over here. So since we have circular plates, what we are going to do is we are going to bring the ruler. We are going to measure the diameter of one of these two plates. Once you get the diameter, now you have the radius. So after you find the radius, the area in that case would be equal to pi r squared. However, since that radius is measured manually, therefore it has a certain amount of error on it, a certain amount of error which is associated with the ruler. And the error on that ruler in that case is going to be the least subdivision that you can read on that ruler divided by 2. So the least subdivision that we can read on the ruler is actually 0.1 centimeter. So that least subdivision you divide it by 2, and that would be the error on the radius. So the error on the radius is equal to 0.05 centimeters. So since the area over here is dependent on r, and on r we have an error, therefore the area is a function of one variable. In that case, you also have to find an error on the area, and therefore the error on the area is going to be propagation of error of that area with respect to its variable, which is r. So you have to do one partial derivative of the area with respect to r times the error on r squared. And then you find the value for the error on the area. So going back to the error on epsilon 0, like I said, epsilon 0 is going to be dependent on slope and on the area. Therefore, to find the error on epsilon 0, you have actually to execute two different partial derivatives. A partial derivative with respect to slope and another partial derivative with respect to area, and therefore you find the error on epsilon 0. Now regarding the relationship relating epsilon 0 to slope and the area, you have to figure it out. You figure it out from that equation over here. You check which terms are actually multiplied by x, and that would be the expression of slope from which you deduce an expression for epsilon 0. That will be for the first part of the experiment. Now moving on to the second part of the experiment, in which we are going to be detecting the effect, or we are going to be studying the effect that the dielectric has on the capacitance of a capacitor. So in the first part, we actually had free space as a dielectric, and we saw that when we moved the plates further away from each other, the capacitance dropped. Now what would happen if we place a dielectric, which is basically a plastic plate, between these two plates? So over here we are going to connect these two plates all over again to that LCR meter. We are going to place the dielectric in the middle, and we are going to bring these two plates closer together until they are at maximum contact with that dielectric plastic plate. So as we can see over here, we have a certain value for the capacitance of 234 or 235 picofarad. So in the table over here, let's say we are going to record that C dielectric, meaning that the capacitance when you have a certain dielectric inserted is actually equal to 235 picofarad. Now over here you have a certain plus minus. What will be the plus minus in that case? The plus minus is going to be the least subdivision that you can read on that LCR meter. So the least subdivision in that case would be 0.1 picofarad. So the least subdivision in that case is going to be 0.1 picofarad. So the error over here would be plus minus 0.1 picofarad, and of course the error or the least subdivision in that case is going to depend on how much decimals you are reading over here on that LCR meter. So for example, if you were reading, let's say, 2 decimals, therefore the error would be 0.001 picofarad. Now there is one distinction that you should make between using a digital apparatus and between using a manual apparatus. In the case of the ruler, we actually divided the least subdivision by 2, whereas over here, since we are using a digital apparatus, therefore we only take the least subdivision. So the error on C dielectric would be plus minus 0.1 picofarad. Now regarding C free space. Now C free space, in that case, what we are going to do is we are going to remove the dielectric material slowly without changing the separation between these two plates. And then we are going to record the corresponding value of capacitance, which is now at 145.4 picofarad. So as we can see, the value for the capacitance, it almost dropped by half whenever we removed that dielectric material, which is an indication that a dielectric material that actually increases the capacitance of a capacitor. So over here you record the corresponding value for C free space, plus minus, in a similar manner, the least subdivision that you can read on that capacitance, which is 0.1 picofarad. Now finally over here they ask you to find the ratio C dielectric over C free space. So you have the value for C dielectric, you have the value for C free space, you find the ratio over here. Now regarding the plus minus, we are going to talk about it in part number 5. So in part number 5, they ask you to find the dielectric constant of the plastic plate along with its error by using the theory of propagation of error. So how can you find it in that case? So we have the following equation, C equal to K times A times epsilon 0 over D. That ratio over here, or that term, it actually corresponds to C free space. So over here we have C dielectric equal to K times C free space. Therefore, K is equal to C dielectric over C free space. Therefore, that ratio over here that we have in the table is none other but the dielectric constant K. So what we are finding over here is we are finding the dielectric constant K. So having that ratio over here, and knowing that we have an error on C dielectric and we have an error on C free space, therefore the error on K would be what? The error on K is going to be now propagation of error, meaning you are going to be deriving K twice, once with respect to C dielectric times the error on C dielectric squared, plus a second time with respect to C free space times the error on C free space squared. But of course, first off, you have to find a certain value for K, and then you find that error on it. That would be for the second part of the experiment. Now moving on to the third part of the experiment, in which we are going to be studying different configurations of capacitors, whether in parallel or in series. If you look over here at that circuit board, we have multiple capacitors. So we have the first capacitor, which has a certain capacitance of 0.47 microfarad. We have the second capacitor, which has a certain capacitance of 1 microfarad, and the third one of 2.2 microfarad, so on and so forth. However, in our experiment today, we are only going to be dealing with the first 3 capacitors. And each capacitor, as you can see, it has 2 terminals, which is logical. Now, if you look over here at the table, first off, they ask you to record the nominal values for C1, C2, and C3. The nominal value meaning the theoretical value or the expected value that you are actually reading on that circuit board over here. So you are going to be recording the first 3 values that you have on that circuit board. Now, in the table, now you have 2 columns over here. You have a column for the measured value and a column for the calculated value. The calculated value in that case is going to be the value which you are calculating manually or mathematically by using the nominal values that you have over here. So for example, for C1, the calculated value would be whatever value you have on that circuit board. For C2, the calculated value as well would be the value that you are reading on that circuit board. And for C3, the same thing, you are going to be recording the value that you have on that circuit board. Now regarding the measured value is going to be the one that you are measuring experimentally. So for that case, we are going to bring 2 electrical wires. We are going to connect one to one terminal of C1 and another connection to the other terminal of C1. And then these 2 connections are going to go into that LCR meter. And we are going to get a certain value for the capacitance, but which is in nanofarad. So we are going to change the unit to microfarad. So we have over here 0.473 microfarad, which is actually close to the nominal value. So over here in that box, we are going to write down that the measured value is 0.473 microfarad. Now for C2, in a simple manner, you are going to move down these 2 connections to C2, to the terminals of C2, and now you have a value of 1.023 microfarad for C2, and in a similar manner for C3, you are going to bring down the connections, and finally we have a value of 2.252 microfarad for C3. So those would be the 3 measured values that you are going to record in these 3 boxes over here. Now moving on to the 4th connection. The 4th connection, they are asking you to connect C1 and C2 in parallel. So whenever you have 2 electrical components in parallel, meaning that they are actually forming a loop, meaning that all of their terminals are connected to each other. For example, let's say over here we have C1 and below it we have C2. If C1 and C2 they are in parallel, therefore that terminal of C1 is connected to that terminal of C2, and the other terminal of C1 is connected to the other terminal of C2, and therefore they are forming a loop, and in that case they are in parallel. So in a similar manner over here, we are going to translate that connection to that circuit board. So one connection from C1 to C2, so the terminal of C1 connected to one terminal of C2, and the other terminal of C1 is connected to the other terminal of C2. And now we branch out two connections from C1 and we plug them in that LCR meter. So as we can see over here, these two connections, they are in parallel. And then we branch out two connections in order to measure the capacitance, which is now 1.497 microfarad. That would be for the measured value. Regarding the calculated value, you are going to find it yourselves. So we have two capacitors in parallel, and you want to find C equivalent in that case. So C equivalent, so you have to find out the right connection, the right equation for C equivalent in the case when you have capacitors in parallel. And then you compare both values, the measured one and the calculated one. And of course, for the calculated value over here, you are going to be using the nominal values that you have. Now moving on to the fifth connection, where you have C1, C2, and C3 all in parallel. So in a similar manner, now to that connection over here, we are going to add C3. And C3 is going to be forming also a loop with the other two capacitors. So both connections of C3, they are connected to C2, and therefore that entire combination is actually in parallel. So over here, what we are going to do is we are going to bring an additional two connections, one from the terminal of C2 to one terminal of C3, and another one from one terminal of C2 to the other terminal of C3. And now we have all three capacitors in parallel, and finally you record a certain value for C experimental, which is going to be 3.750 microfarad. That would be for the measured value. For the calculated value, you are going to calculate it yourself by finding C equivalent using the nominal values that you have over here. Now regarding C1 and C2 in series, moving on to C1 and C2 in series. Now when you have two electrical components in series, meaning that not all of their terminals are actually forming a loop. So they are not sharing all of their terminals, but rather they are sharing only one terminal. So we have C1 over here, and we have C2. Therefore, one terminal of C1 is connected to one terminal of C2. However, the other two terminals, they are going to be free to be connected to whatever other electrical components. So for example, let's say they are connected to a voltmeter, or they are connected to a power supply, or they are connected to the LCR meter. So as we can see over here, C1 and C2 in series, meaning that they are sharing only one terminal with each other. So on that circuit board, so over here we are going to bring one connection from the terminal of C1 to the other terminal of C2, and then we bring out two connections from the terminal of C2 and from the terminal of C1, and we plug them into that LCR meter. So as we can see over here, we have C1 and C2 in series with that LCR meter over here. So in that case, we are going to read a certain value of 0.323 microfarad for the combination of C1 and C2 in series. And then in a similar manner, over here you are going to find C equivalent, which is going to be calculated mathematically by you by using these nominal values that you have over there. Now moving on to the connection of C1 and C2 and C3 all together in series. So if they are all in series, therefore, we can take the following connection. We can take a diagonal one. Like you can manipulate with the connections however way that you want, but the main thing is that you have them all correct. And then one connection from here to C3. So we have C1, C2, and C3, and then these two connections would be taken into that LCR meter. So one connection from C1 to another terminal of C2, and then one connection from the other terminal of C2 to the other terminal of C3. So now we have C1, C2, and C3 all in series. As you can see, they are all in series. And finally, we take, or we branch out two connections from C1 and from C3, and we plug them into that LCR meter. And over here we have a value of 0.283 microfarad for the combination of C1, C2, and C3 in series. And of course you have to find C equivalent for them by using the nominal values. Then before the last combination we have over here C1 in series with a combination of C2 and C3 in parallel. So first off we are going to start by connecting C2 and C3 in parallel. So we have C1, we have C2, and we have C3. So C2 and C3 in parallel, meaning that they are forming a loop. All of their terminals are connected together. Then you have C1 in series with them, meaning that C1 is only sharing one terminal with them, while the other terminal would be connected to the LCR meter. And that would be it. So over here we are going to start by connecting C1, C2 and C3 in parallel. So now we have C2 and C3 in parallel. Then we bring one connection from C1 to C2. And finally we branch out one connection from one terminal of C1 and into the LCR meter, and another connection from C2 and into that LCR meter. And finally, we have a certain value of 0.413 microfarad. That would be the measured value over here, but of course you have also to record the calculated value, or you have to calculate the calculated value by using the nominal values that you have. For the last connection, you have C1 and C2 in series, and that combination is in parallel with C3. So we have the following: C1, C2, and C3. So first off, we want C1 and C2 in series. So one connection from C1 to C2. Now they are in series, they are only sharing one terminal. However, we want C3 in parallel with that combination. For C3 to be in parallel with them, meaning that C3 is going to share both terminals with these two electrical components over here. So one terminal of C3 is going to be connected to one terminal of C2, and the other terminal of C3 is going to be connected to the other terminal of C1. And therefore we have C3 in parallel with the combination of C1 and C2 in series. We can draw it differently in order to understand better. So you have C1 and you have C2 in series. For C1 and C2 to be in series, meaning that they are sharing only one terminal and not all the other terminals. And for C3 to be in parallel with them, meaning that C3 is actually sharing both of its terminals with C1 and C2, and therefore as you can see we have C1 and C2 in series. However, that combination is in parallel with C3. So we are going to do the same thing over here. We are going to replicate that connection. So we are going to start by connecting C1 and C2 in series. C1 and C2 in series. Now, like I said, we have to make sure that one connection of C3 is connected to one connection of C2, and the other terminal of C3 is connected to the other terminal of C1. So one connection, we take it out from one terminal of C3 to one terminal of C2, and the other connection would go from the other terminal of C3 to the other terminal of C1. And now we have C3 actually in parallel with the combination of C1 and C2 in series. And finally, we branch out two connections from C3, and we plug them into that LCR meter in order to get a measurement. So over here we have a certain value of 2.576 microfarad for that combination. That would be for the measured value, and for the calculated value, like I told you before, you have to calculate it yourself by using the nominal values, by finding C equivalent of that combination. That would be for the third part of the experiment. Now moving on to the fourth part of the experiment, in which we are going to be exploring the capacitance of the coaxial cables. So over here, if you look at the coaxial cable, it actually consists of an outer cylinder and an inner cylinder. So these two cylinders, they are basically conductors and they are parallel to each other. Therefore, that coaxial cable, it has its own capacitance that we need to measure. Moreover, why do we call it a coaxial cable? Because it actually has a common axis at both ends. So over here we have that axis in the middle, which is common with the other end of that coaxial cable. Now, in order to measure the capacitance of that coaxial cable, we have to be using an adapter. However, that adapter, it also consists of an outer cylinder and an inner one, which are both parallel to each other. Therefore, that adapter, it also has its own capacitance that we need to measure individually. So for that matter, we are going to plug that adapter in the LCR meter, and we are going to get a certain value for its capacitance, which is 0.7 picofarad. So over here in that table, we are going to be recording the capacitance of the adapter of 0.7 picofarad. Now regarding the plus minuses, you can forget about them because we are not applying any propagation of error later on in that part. Now, we need to measure the capacitance of cable 1 with adapter and without adapter. So, with adapter meaning that we are basically bringing that coaxial cable and connecting it to that adapter, and therefore we are getting a certain value for the capacitance of 96.7 picofarad, which is going to be the capacitance of both of the coaxial cable plus the adapter. So in that box over here, we are going to record the value of 96.7 picofarad, which is for both, for the capacitance of the adapter plus the coaxial cable. Now we want the capacitance of the coaxial cable without the adapter. We already have the individual value of the capacitance of the adapter. We subtract it from that value, and we get a value over here for the capacitance without an adapter. Then we are going to repeat the same thing for cable 2. So we are going to bring a different coaxial cable, and all over again we are going to connect it to that adapter, and we are going to get a certain value for it, which is now at 120.7 picofarad. So over here in that box, you record 120.7 picofarad. Then you want to find the value of the capacitance of the coaxial cable without an adapter. So you subtract both values. You subtract that value from the value of the capacitance of the adapter. They ask you to join cable 1 and cable 2 together in order to find their entire capacitance. For that matter, we brought over here a connector. We connected one end of cable 2 to that connector and the other end of that connector to cable 1. Therefore, we have cable 1 connected to cable 2, and both are connected to that adapter and plugged in that LCR meter, and therefore over here we have the entire capacitance of 243.4 picofarad. Now, in the next question, they are asking you if cable 1 and cable 2 are actually connected in parallel or in series. In order to answer that question, over here you have the individual capacitance of cable 1 and cable 2. If you add them together, and if the total capacitance would actually equal the capacitance of cable 1 connected to cable 2, therefore cable 1 and cable 2 are in parallel. If not, therefore they are in series. So the point over here is, first off, to find the entire capacitance of cable 1 being connected to cable 2, then to deduce if they are in parallel or in series. And in order to deduce that, you already have the individual capacitance. You try to add them up. If they add up to that total cable 1 plus cable 2, therefore they are in parallel. If not, you would deduce that they are actually in series. Now in part 11, they ask you to find the dielectric constant of that coaxial cable. As we have seen before, that coaxial cable, it has an outer cylinder and an inner cylinder. So it has an outer diameter and an inner diameter. And over here they have given you actually the ratio of the diameters of that coaxial cable, which is D over A equal to 2.97. Now, if you go back to the manual, you have a specific equation which is actually specific for a cylindrical shape for that coaxial cable, which is derived by using Gauss' law. So by using that equation in the manual, you already have that ratio of diameters. You pick either value for the capacitance, either for cable 1 or cable 2, it's not going to matter. You plug in all the missing components that you want, and finally you arrive at a certain value for the dielectric constant of that coaxial cable, which you are going to compare later on to the expected theoretical value. And that would be it for our experiment of today.